All right.
Right, guys. Welcome to the Spark Lab group meeting. It's a great pleasure today to have a guest speaker. So Shreyas Kousik is visiting us virtually and is giving a presentation about his PhD work. Let me do just a quick introduction and then we'll just jump right in his presentation. So Shreyas is a PhD candidate in mechanical engineering at the University of Michigan. He's working with Ram Vasudevan in the ROM lab. And previously I studied at Georgia Tech and did internship at NASA, Nissan, and General Motors. So I became interested in autonomous cars, safety, and recently is exploring essentially safety for mobile robots in general. And as you will see, he really likes exploring mathematical ties that connect different robots and control algorithms to enable real-time safe motion planning. He's been the recipient of a number of awards, like NSF Graduate Research Fellowship, Best Paper Award. So it's a huge pleasure to have him here give a presentation in Spark. And in other contexts, we would welcome you in a different way. I guess that's like a virtual welcome we have to give. So take it away and thanks for being here.
Yeah, thank you for inviting me. This is really great. So hi everyone, I'm Shreyas, and I'll be talking about how to generate motion plans that come with a certificate of safety. The big hammer I use has been reachability analysis. And the reason I'm doing any of this is that I want robots to be able to navigate cluttered, complex scenarios like traffic jams, or even maybe a crowded kitchen where there's a real risk of either hurting the robot itself or hurting other humans. And I want robots to be able to take over jobs that are dangerous or that humans don't want to do. All of these tasks, as far as I can tell, require robots that are in some metric safe. So we have to specify safety mathematically. And as we're all familiar with, one way to stay safe is to stay home right now. But a robot that just stays home indefinitely will never do anything. So we can't be too conservative, meaning the robot should be live. It should be able to go out and do stuff in the world. The framework with which I've approached these problems is called receding horizon planning. And I'll use this cartoon drone to illustrate throughout the talk. Note that anything that I show you as a cartoon can be translated rigorously into mathematics, but I like to illustrate things and animate things for your understanding. I'll also point out if the animations are really laggy, they are smooth on my end, but there might be connection issues. So I've shared the slides with you if you want to reference later. So imagine this drone, some obstacles in the world, and then some global goal that we care about it reaching. Because the sensing capability of any robot is limited, we typically say that it has a limited sensor horizon, or a distance away from the robot within which you can see. And the strategy is then to plan a short trajectory, and then while executing it, plan our next short trajectory. So the sensor horizon is receding away from the robot. Eventually, hopefully, you can reach this goal location and not crash into stuff. But as shown in this cartoon, where the blue line, the solid line is the executed trajectory and the dashed line is the reference trajectory, we have tracking error because we can never perfectly plan in real time. And to compensate for this tracking error, one naive approach is to say, well, I know what my worst case is going to be. Let's say I have Lipschitz continuous dynamics or something like that. And then I just grow all my obstacles by that amount and say, okay, as long as I plan outside these obstacles, I should be okay. This can work really well for example, a drone flying above a city. But if you want to fly around in a city and really interact near and around people, this may be too conservative. Everything, all your free space might be taken up and you might not be able to find a plan. There are a few ways to deal with balancing safety and conservatism. And I'll break down how planning is generally approached in robotics. At the top tier of a three-tiered planning hierarchy, we think of a path planner as more or less ignoring the dynamics of the robot or using an extremely simplified representation and then trying to really rapidly find a path through the world. So like an RRT is a really good example. The output of a path planner is passed to a trajectory planner to generate a dynamically feasible reference trajectory for the robot to track with a tracking controller. And then the job of the tracking controller is to respect the dynamics of the robot, the input constraints, and then minimize tracking error. You could attempt to enforce safety at any of these tiers, and I'll give one example of each. So at the path planning tier, a state lattice approach uses parameterized paths. So the space on the left contains parameters. That's usually like a n-dimensional Euclidean space. And then the space on the right is, let's say, the workspace of the robot, X. And these reference paths are the dashed lines. The idea would be use a very simplified model of the robot. And then when obstacles appear at runtime, you can eliminate paths that are potentially in collision. These types of methods use really simplified descriptions of the robot to produce paths really quickly, which is good for like almost like a Google Maps approach for an autonomous car. But then it's hard to say something about safety when you're not trying to accurately describe where the robot's going to go. In other words, there's a trade-off, how much you want to increase the size of obstacles or respect the dynamics of the robot. That's why typically we want to talk about safety at the trajectory planning level, and that's where my proposed method also lives. A good example actually from MIT is the funnel library approach. So here, the space on the left you can think of as a space of trajectory parameters, and any point in this space, so like this point corresponds to this, now it's a reference trajectory, the dashed line, and then let's say that we have some tracking error given by the solid blue line. The goal with this approach is to compute reachable sets or funnels that contain everywhere that the robot, subject to the high fidelity, accurate description of its dynamics, would go despite trying to track these parameterized trajectories. And offline, you would do a reachability analysis step to compute a family of such funnels, as they're called. Then at runtime, you eliminate funnels that could cause collisions and select from the remainder. So in this particular instance, you would pick one of these two and know that it's safe. This actually works very well. However, picking a finite library a priori could limit your planning options, especially if you wanted to use this potentially for like a robotic arm or something that's really high dimensional. Finally, you could let the path planner and the trajectory planner do whatever they want and say, okay, my tracking controller will be safe. An exemplary approach here is called the fast track method. The idea is to pre-compute, again with reachability analysis, tracking error, which is going to be this axis on the left, by allowing your planning model to do anything you want, tracing out, for example, a cone of possible plans as time goes to infinity. And the reachability analysis in this method computes the amount of tracking error in position, let's say, as well as an associated feedback controller to keep that tracking error bounded if you can choose your model carefully. So here's just one example, arbitrary plan, and then the tracking error stays close to it if you use the associated feedback controller. At runtime, we take this amount of tracking error that we've computed and use it to dilate obstacles. And then no matter what our planner does, as long as it lives outside of obstacles, our car should be safe. This works pretty well as long as you can select your models carefully, but treating your planner as this disturbance that's allowed to do anything is quite conservative, because in some sense your planner and your robot are fighting against each other. So to summarize the challenges here and introduce my method, which is called reachability-based trajectory design, it's hard to say something about safety when you're using a simple model of a robot. It's not impossible, it's just hard. Pre-specifying a finite set of choices might limit what you can do. And then treating your planner as a disturbance can pit your robot and planner against each other and introduce conservatism. My method, RTD, uses a simple model and an error model together to compensate for the fact that a fast model that we can use for planning or a simple model that we can use for really fast planning isn't a perfect description of the robot. I use a continuum of parameterized trajectories, which frees up a lot more options than a finite library a priori. And I use trajectory dependent tracking error so that instead of padding everything uniformly and then limiting free space, the idea is I want to do my padding in the best possible way, in some notion of optimality. That completes the background of the talk. The rest of the talk is a high-level overview of RTD, and then a discussion of the offline reachability analysis and the online planning, and then I'll zoom out. Again, feel free to interrupt with any questions.
Very quick question just about the background. So for fast track, you mentioned that you have to choose the model carefully. What are the assumptions there?
There are a few. So you can get away with discontinuous things because they have to discretize in their implementation. But to prove anything, they need Lipschitz continuous dynamics. It's tricky because they actually let time go out to infinity. But again, in practice, they discretize, so they just go out to like however long. The biggest, most difficult assumption to satisfy is that your high fidelity model can actually catch your planning model when your planning model is allowed to do anything. That's easier to satisfy for like a Dubin's car, but at least when we were implementing a comparison with that method, what we found is that if you're not very careful about making sure your high fidelity description can catch your planning model, like a cat and mouse game, then your conservatism explodes. So it's still safe. It's just that your robot says, I'm not going to move, and it stays still. Luckily, the folks at Berkeley were very helpful and kind in like helping us through their code. So we were able to get it working, but it takes some care.
Got it. Okay, thanks.
Any other questions? Okay. So how does RTD work? Let's look at this plot again, and I'll walk through the drone for this whole talk, the quad rotor example, but I'll show you some videos of other robots. Recall that a point in this parameter space, K, creates a trajectory in the space X, the workspace of the robot. And we have tracking error. So our goal is to hold on to a reachable set of the robot that contains the trajectory and the robot's motion despite tracking error. But we don't want to do that for one trajectory. We want to do that for a continuum of trajectories, resulting in a set that I call the forward reachable set. And we want to compute this offline. At runtime, we'll do the following. Given obstacles, we can intersect them with the reachable set in X and project that intersection into K to find parameter space obstacles. These have to be computed at runtime, because then what we can do is, given an arbitrary trajectory optimization cost function, we can solve a problem like this. So we want to find the best little k in the space K, given some arbitrary cost such that we're safe. That's what this means. And then the k sub u means unsafe. So this is what we're solving in each receding horizon planning iteration. We'll map these obstacles, solve this problem, and then pick, for example, one trajectory, and know that as long as it's a feasible solution to that program, we're safe. We would rinse and repeat each time the robot moves a little bit. So solving this program should occur at like 2 to 4 hertz to generate trajectories in practice. So what does it actually look like? Here's a simulated drone flying through a randomly generated forest. And because of the model we chose, we were limited to 5 meters per second, which is the speed under which you can ignore many aerodynamic effects. Over hundreds of such trials, we were able to, well, we had 0 crashes and were able to reach the goal quite often, or stop safely when we can't reach the global goal. We've also begun doing this on hardware. So now you can see our lab. And then here's this little tiny Parrot Mambo mini drone. The idea is, and I'll pause the video right when we see the reachable sets. So here you can see a reference trajectory as a blue dashed line. And then the reachable set is this series of boxes. And I'll talk about this representation in more detail going forward. But one thing—
if I can interrupt you,
yeah.
Sorry about that. I have a question on the chat from Hank. Hank is asking, what are the parameters for the trajectory? So on the Euclidean space on the left-hand side of the previous slide, can you give an example of it?
Yep, that's actually coming up. So this is just to tease you and make you interested in the with a bunch of videos. I'll show you again the parameters shortly. So here, just to convince you that this really does work on a variety of robots, here's a little rover in lab. Here's the robot. This is what the robot is seeing. And we've used a planar LiDAR to detect obstacles. This contours the reachable set for the particular choice of trajectory parameters at the current iteration. And then here's a GoPro mounted to the robot. And the robot is trying to reach this black star. Over many such randomly generated trials, the robot's able to navigate up and down the road over and over and over. And this is me with short hair, wow. So our most recent result, and I know I'm now teasing you at this point without showing you what the parameters are, but I'm very proud of this work. From earlier this year, we have this robot arm under the table, and we're telling it to go above the table. In this case, we deliberately wrote a really bad path planner. So the path planner just tells it to move the end effector, and then it gives it intermediate poses for the arm that are in collision with the table. And I'll show you what one of those looks like right now. So here you can see these black versions of the arm are the intermediate pose. The blue arm is the current state, and then the gray blob is the reachable set. And this black arm is living inside the table obstacle. And basically RTD is just waiting for the high level planner to give it something reasonable to do and trying its best to track these trajectories that are inside the arm or that are inside the table. as soon as the arm finds a trajectory on the other side of the table, we're able to rapidly get over there without crashing. And this is also to illustrate that we're not super conservative. All right. Now I can talk a bit about the models we use. So this will answer Hank's question of the trajectory parameterization, and then I'll talk about how we do reachability analysis. For the drone, we use a model that looks like this, which has a position, velocity, angular velocity, and the body frame to inertial frame rotation matrix. We can write down these dynamics, which are the standard 3D rigid body dynamics for a drone. And really what's important to look at here is we have a thrust input aligned with the E3 or Z axis of the drone, and then a body moment produced by the differences in the rotor speeds. This can give you a pretty accurate description of how a drone will move through space, but it's very hard to plan with this type of model at runtime, partially because we're evolving not just in Euclidean space, but also on SO3. Here we have a rotation matrix. So to do a plan, we use the simplified model, which again, points in this space on the left are trajectories in the space on the right. I'll use little f to denote this planning model. And in particular, this model specifies the desired velocities. So this p dot desired, which is a function of time and parameterized by k. The form we use is common in trajectory planning for drones, and that it's in the 3 separate dimensions of workspace. It is a, here we go, 3 separate dimensions of workspace. It is a time varying polynomial with coefficients. The first, this is the dimension, and then this is the degree of each coefficient, and that's what's parameterized by k. Importantly, these dynamics are decoupled in, let's say, x, y, and z, or these 3 dimensions, which allows us to make reachability analysis tractable. So where do those coefficients come from? The particular, the choice that we made was that our parameters are our initial velocity, our initial acceleration, and our desired velocity at some time during the plan, which we specify a priori as this t desired. The other thing we specify is that our velocity and acceleration at the end of every plan ends in a stop. This way, as we're doing receding horizon planning, if for some reason in one iteration we can't solve that program to a feasible, we don't converge to a feasible solution, our previous trajectory ended in a stop. So we can at least begin stopping. So I hope this answers your question of, in the case of the drone, what is a good parameterization? I'll point out that the parameterization like this, we found it to be useful for our particular task of navigating these arbitrary obstacle scenarios. We can use other parameterizations. This particular one, because the drone is described by that nasty high fidelity rigid body dynamics, this parameterization will become very useful for computing reachability analysis on that high fidelity model shortly after this. All right, so how do we do reachability analysis?
I have a quick question, Shreyas. If you can go back. So is I guess, if I'm thinking about polynomial optimization here, you're giving like the initial position, the initial state, the final state, and an intermediate waypoint, right? Mm-hmm. Is the final state actually the end of the entire trajectory, or you're doing this in a kind of receding horizon MPC style?
I'm not sure I perfectly understand your question. So are you asking if we're optimizing portions of the trajectory and then
exactly.
like,
yeah.
In each receding horizon iteration, it's slightly different from MPC in that we generate the entire trajectory every time. And that's where you could use MPC much more effectively to track the trajectories that we generate. So I'll show you an example with a full-size passenger sedan later, where that's how we actually did trajectory tracking. But using MPC to generate the trajectory in a receding horizon way turns out to be usually too slow without a bunch of simplifications of the model.
Okay, but just to make sure I understand, this kind of segment that you're showing on the right, in which there is the initial point, final point, and the intermediate waypoint, you have a bunch of those segments to cover the entire trajectory.
No, well, I guess since we're playing in real time, we'll generate one of these small trajectories every planning iteration, and we stitch them together as the robot.
Okay, good. Yep. Yeah. Okay, thanks.
Okay. Yep. Cool. All right. So before we dive into the reachability analysis, I'll talk about this object called a zonotope, which is a set in Rn centered at a point C, and I'll call it big Z. A zonotope is constructed by the convex combination of this point C, the center, with generator vectors G, so G1 shown here. And then as you add more generator vectors and multiply each one by an interval in -1 to 1, you can trace out a convex polytope. This is a particular type called a zonotope. This object is really useful because on a computer, all we have to hold on to is the center and then a generator matrix, which is just this concatenation of the generators. And then implicit in the representation is this multi-dimensional interval B, which is from -1 to 1 for each generator. Another really useful property is that the Minkowski sum, or the set addition of two zonotopes, is the sum of the centers and then the concatenation of the generator matrices. And then B1, B2 here is in MATLAB notation just to keep track of these intervals. This is really useful because if we can represent our reachable set with zonotopes, we can compute a reachable set for our planning model and for our tracking error separately, and then add them together and create a reachable set for our high fidelity complex description of our quadrotor. So first, I'll talk about the planning model reachability. The goal here is to compute these sequences of zonotopes that represent the reachable sets of our planning model. We make use of an open source toolbox called Cora, and I'll point out a GitHub link later if you want to see some of our code. What Cora is doing under the hood is this for a single parameter. Suppose that I chose one, and then I have Z0 as an initial zonotope. And my time horizon here is some T0 to TF. What we do is we partition time into a bunch of small intervals and then compute a zonotope that provably contains the motion of the planning model in each of these n intervals. What that looks like is an Euler integration step that shifts the zonotope according to a linearization of the planning dynamics, and then a dilation or buffering to compensate for linearization error. If I were to plug in the high fidelity nonlinear model of the drone, this linearization error would explode. But because we use these simplified polynomial dynamics for the planning model, this linearization error is actually quite small. And we end up getting a pretty tight sequence of zonotopes, which is this reachable set just for this parameter K star. And again, n comes from this partition of time. But we don't just do it for one parameter, we do it for this continuum. So our initial zonotope is defined as the entire set K and this box around our quadrotor. And then Cora will spit out this sequence of zonotopes, if the animation works, there we go, which is then our representation of the forward reachable set that we want to use for planning. One point in this parameter space, again, will back out a smaller sequence of zonotopes. So we can take subsets of this really high dimensional object and find just the reachable sets we care about. In other words, what you should really take away from this is that we have a reachable set for our planning model, represented as a sequence of zonotopes. And now all we need to do is add the tracking error using that Minkowski sum property from earlier. All right, so now how do we do reachability for the tracking error? This is quite a lot harder. We have the simplified 3D dynamics plus the 9 dimensions of our parameters, which have 0 dynamics. And then we have this really nasty nonlinear model, which depending on how you want to represent a rotation matrix, may be either 9 or 3-dimensional. So we have to do reachability. These two share the position, but we have to have 9 plus another potentially 3 dimensions and time. So that's a really high dimensional nonlinear model to start to assess. And the reason we have to care about the entire model is that our tracking error is our position of our actual quadrotor minus our desired position. So we have to perform reachability analysis on a high dimensional nonlinear system. A common approach to at least give this a shot would be sampling. In fact, we do sampling, but you can't just sample in a 22-dimensional space and hope for the best, because the curse of dimensionality really gets you. So we specify how to choose the samples to compute tracking error maximally. That requires a common assumption in quadrotor dynamics, in that the rotation dynamics are much faster than the translation dynamics. So the takeaway here is you can point your thrust vector quickly in the direction that you want to, and then you apply an acceleration that operates at, in some sense, a much slower rate. But this allows us to linearize the dynamics to assess where our controller performs the worst. And that is in particular the tracking error is maximized when the initial speed or the magnitude of its initial velocity is at a maximum. The takeaway here is we don't need to use the linearized model to compute tracking error, but we do need to use it to identify where to sample this high dimensional space to make computing tracking error tractable. This that I'm presenting is particular to the drone, but in general, because we're parameterizing our trajectories a priori, we can use properties of that parameterized trajectory space to determine where tracking error will be really bad. For example, for the wheeled robot, we know that a larger change in our desired yaw rate will produce larger tracking error. So we pay a penalty in that we are limited to a parameterized space of trajectories, but we get a big win in the sense that we make computing a reachable set for a high fidelity model much more tractable. And before I go through how we actually do this computation, let me remind you that our planning model has parameters for initial velocity, initial acceleration, and desired velocity at a point along the trajectory, where t desired is fixed. So our goal is to estimate the tracking error or to do reachability analysis on our high fidelity model as a function of our initial velocity by varying our desired velocity. And these are the spaces we're sampling. So instead of sampling in this really high dimensional space, we just have to sample initial velocities effectively. To show you how that works, I'll build the algorithm here. So imagine our drone and then this sphere of possible velocities with radius v max. The algorithm we want to build starts by over approximating the sphere with the box. And again, all of these cartoons turn into rigorous math, but I just want to get the point across. This box can be represented again as a multi-dimensional interval with some corners. So these are bounds that specify the corners of this box. And for each of those corners, which we can look at one right now, we can choose samples in our desired velocity coordinate. And again, I hope that this isn't too confusing, that these are all velocities that you're looking at, not positions. My lab mates were a bit baffled by that. So just remember that all of these yellow and orange objects are velocities. Given any initial velocity, we can choose essentially a sphere of possible desired velocities that are our initial velocity plus some maximum allowed acceleration times our desired velocity time, right? And again, we can over approximate this with the box and then choose the corners of it. And this is exactly how we've generated samples to figure out where our tracking error is maximized. So for each of these initial velocities and each sample, then we can actually run forward those high fidelity dynamics and take the tracking error directly and save a zonotope that over approximates or takes the maximum in the 3 spatial dimensions of the difference between our planning model and our high fidelity model. We also index these zonotopes by the time horizon or the time intervals that we use for the planning model reachability so that we can use that Minkowski sum property. Are there any questions on this part?
So I see a couple of questions on the chat. Andy was asking, how do you decide the t desired, which is the instant of time in which you enforce the velocity?
All right. So usually t desired is in the same way that I showed here. We have this a max. So we know that there's some maximum acceleration we want the drone to be able to achieve. So we can say, okay, our a max is our, we solve this for t desired given some allowed maximum speed. So replace v desired here with v max and v naught with 0. And you can determine t desired based on what you've decided is your maximum acceleration and velocity allowed for your drone. In practice, t desired is 1 second, and then the whole trajectory is 2 seconds. So we could go up to our max speed and then break back to 0 from it. And we're playing many of these 2 second long trajectories in a chain as the robot is flying. And I figured out how to pull up the chat. So should I look at these questions now? Is v desired defined over all time? So v desired is defined at a single time during the trajectory, and we have v naught and we accelerate up to it and then break down to a stop. So you can think of this as like a peak speed for that particular small trajectory. And then by chaining together many peak speeds, potentially in different directions, you can go around obstacles.
So I think you addressed all the questions except the last one. I already asked the other ones. Okay.
The initial velocity and acceleration are free parameters for the reachability analysis, but we don't achieve arbitrary ones at runtime. So those we estimate from the robot and then plug those into our reachability analysis. What that means is that for trajectory optimization, we're actually only optimizing over V desired here. We're not optimizing over V naught or A naught. All right, let me, I hope that answers everybody's questions. Oh no, I scrolled past my slide. Hold on. All right. The big takeaway here is that suppose that that assumption is true, that our rotation dynamics are much faster than our translation dynamics, then at any moment in time, our actual robot, the high fidelity model, is in the planning model reachable set plus the error zonotope. So our actual robot position lives inside of our planning model zonotope plus this error zonotope, and that's only a function of our initial velocity. In other words, we've taken this really high dimensional system and made it tractable for reachability analysis, and now we can hold on to sets that represent where our actual drone will go. Now we can use these objects for planning at runtime. First, we want to map them into the parameter space, and then we want to do trajectory optimization. What that looks like is when obstacles appear, we want to identify the set K sub U for unsafe. And to illustrate this, I'll just show a single time interval from our partition of time, which is the ith one. I'll also replace this zonotope plus error with Z hat, which is still a zonotope because the Minkowski sum of two zonotopes is still a zonotope. And now what we care about is assume that our obstacles can be represented as zonotopes, which is reasonable for like voxel grids or octrees or certain convex decompositions of space. Then is this intersection non-empty? If it is, we can project the obstacle into the parameter space and use it for online planning. I'll start to gather math on the left-hand side for your reference and then work the math on the right. So checking that intersection, recall that we can write our zonotope as a center and a generator matrix. And similarly, with multidimensional interval B. And similarly, we can write our obstacle as a center and generator matrix by our assumption. Then to check the intersection, we can solve this equation for an interval BU, again for unsafe. And that might look something like this. So BU here is just some multidimensional interval, not necessarily between -1 and 1. Recall that the zonotope is defined by this interval B from -1 to 1 in each dimension. The trick here is that we can compute BU really quickly with a matrix inverse and then check if these two intervals overlap. If they overlap, then we have unsafe trajectories that we want to avoid choosing from. And that's exactly what we can prove is that if we have unsafe trajectories, then these intervals overlap. The really useful part is that we can evaluate if our decision variable at runtime, or K, is in this unsafe set. That's equivalent to checking if a point is inside a polytope. So checking if the maximum of a bunch of linear constraints is positive. And because we're using polytopes, you get gradients as well. So your trajectory optimization can run really quickly at runtime. The nice thing is that this intersection of the intervals gives us that polytope. It gives us, it gives us all the half planes defining it because we have taken this intersection of intervals. Okay, so what does that look like? Well, suppose that we have our drone and then we've estimated our initial acceleration and initial velocity, and we were following a trajectory from the previous iteration. And then suppose that we've mapped our obstacle into this space for the current iteration. Then what we can solve is, again, this problem. Pick a K that's not inside this set KU for some arbitrary cost. And as long as we find a feasible solution, we know that it'll avoid the obstacle, that the actual drone will avoid the obstacle. To make this tractable, we have to assume that we can start out in a safe position, like hovering, and then we can say the robot will never crash. This is the big takeaway. Like, now we can say, yes, I can do receding horizon planning, I can generate trajectories, and despite the fact that I can't track them perfectly, my robot is safe. However, we haven't done that just for a drone. As I showed you a bit, we've done that for a few different robots. So here is a car simulation of an autonomous car, and it's driving around a 1 kilometer test loop at up to about 35 miles per hour, which is just the speed limit of the road, is the only reason we picked that speed. And you can see these reachable sets are quite long because it's traveling quite fast. The cost function is saying just go down the road as fast as you can. And you'll notice that the car slows down naturally to take corners, which is, we didn't program that in, it just happens because the reachable sets are only feasible when you slow down. The goal then is to drive this test loop over and over and over, and we did that hundreds of times with no crashes. This is also using, again, a really, really high fidelity simulator. So it's the closest we can get to reality right now. We're working on the real car. We've also incorporated dynamic obstacles. So here you'll see our drone, and this rover has a stick on it that will hit the drone. We're forcing the drone to fly low enough that it's actually in danger. And the drone waits patiently for the rover to drive by and then zooms past as soon as the area is clear. In this case, we're giving our drone a prediction of the rover, which we pre-programmed, just because we only want to illustrate how RTD can react to dynamic obstacles. To visualize that a little bit better, here's our Segway robot driving around the atrium of the mechanical engineering building, and we gave it virtual obstacles. So we told it where these obstacles are. And despite the obstacles not reacting, so the obstacles don't change what they're going to do relative to us, so they can crash into us if we're not careful. But we're able to more or less wait until they move out of the way because they're being quite mean and get to the goal reliably. And finally, this is the riskiest demo we've done yet, I think. So this is the fetch arm planning, and then whoop, a glass vase pops up that Ram bravely donated, and then we stuck motion capture markers too. And at the end, I sped it up to get you to see it get all the way to the goal. But the idea is we trust this thing to not hit stuff. And now we're on the way to doing reliable planning in arbitrary environments that are even potentially moving. But there's a huge part of this that I haven't talked about. And in all of these scenarios, what is required is that the robot correctly senses the world around it. But I've only talked about how we plan. So what I really want to do, and what I need to learn more about for my own satisfaction, is how does the robot perceive the world around it? I'm pretty confident on this part. I can generate plans that will not crash, but this is the question that's left to answer. A few things that I'm starting to work on that I'm curious about are safe mapping, moving away from these deterministic descriptions of our robots to do reachability in a data-driven way, and then using the fact that as a controls engineer, I tell you, this is the representation I need for safety, and using that to guide how a perception algorithm operates. So I'll just do one little slide on each of these, but the big takeaway with RTD is that we don't need a global map to ensure safety. We just need to know what's immediately around the robot, and then we can create safe plans. This allows you to arbitrarily switch out your path planner, and ideally, you can trust that the robot will be safe and then go explore, send the robot out into an unforeseen environment. My dream demo here is to just point a drone at a forest and have it fly perfectly through the forest on the first try. On the other hand, throughout this talk, I've assumed that we know that model of the drone, but that's not always true, especially as the battery changes or thrust changes. So I really want to soften the boundaries of these reachable sets and use robust statistical methods to understand exactly how much risk I'm willing to tolerate. The other thing is that because of the representations I've been looking at, especially these zonotopic representations, we can update and modify our reachable sets as our dynamics change at runtime. Unfortunately, this means sacrificing some strict guarantees of safety probably, but I believe that we can strike a nice balance where we're able to update the dynamics of our robot at runtime. And finally, imagine that we had some arbitrary obstacle, and what I've told you so far is that we need zonotopes, right? Often you can generate zonotope-like objects, but more broadly, what my research has done is specify some minimum amount of information I need as the planning engineer to tell you that your robot is safe. And what I'm excited to learn about next is how do I generate that information and not waste any computational resources on anything else? I want to generate the least amount of information needed to complete my task. With that, that wraps up everything. And actually that was a little bit faster than usual. So I must be talking fast. I'd like to thank all my lab mates. There's been a whole bunch of people. I'm not a solo effort on this at all. And then obligatory funding. And there's a whole bunch of GitHub tutorials. So if you look at that PDF of these slides, you can also go find these. In particular, if you care about the zonotope stuff, look at the Zono turtlebot example. And that does all of the same math that's in this presentation, but for a ground robot. With that, I'm happy to take questions, and I'm excited to see what people think.
Very cool. Okay. Thanks, Shreyas. I'm virtually clapping my hands, as you can see from the screen.
Thank you, thank you.
I guess that's the best we can do in this setup.
Right.
Thanks for the talk. Was super interesting. I have a few questions on my side, but maybe let's open it to discussion. Like, if you guys have questions, maybe you can either just go and try to ask the question, or you can raise your hand.
I think I also have the chat pulled up, so if you want to just type in the chat, or
yep.
you can unmute yourselves if you really want. Oh no, I answered all the questions already, it seems like.
Oh, I do have questions on my side. So
Okay.
let me start maybe, and let me start with a few questions. Let's see. I have two. Maybe let's start with something about the drone dynamics and the assumption about looking at this decoupled representation with the X, Y, and Z of the drone being somehow decoupled for the zonotop representation. Did you look at the literature on differential flatness? Did you see some connection there? Because for polynomial optimization, that's what they do, right? They essentially leverage differential flatness to decouple in terms of X, Y, Z, and U. Yep. Which is fairly similar to, I mean, it's like a little bit higher dimension of what you're doing, but it's pretty close.
Correct. And we actually do use the Mellinger and Kumar controller, that original differential flatness. So RTD is a trajectory planner, and then we use their tracking controller. But their tracking controller, actually, there's work from Tae-Young Lee at George Washington University that proves that using certain if you write your controller directly on SO3, you can say, given a finite trajectory and a finite or a certain bound away from it, you can actually converge to it. And so at least it's reasonable to say that under these types of controllers, you will stay close to your trajectory. And that's exactly what we make use of to make that tracking error computation tractable. In the sense we know that our dynamics aren't going to explode away from them. To directly answer your question, we are using the exact same polynomial representation as Mellinger and Kumar, Rafael D'Andrea at ETH Zurich. Actually, Jesus Tordesillas in John Howe's lab is also using this very similar representation. I think Nick Roy and Andrew Richter also used it. So like everyone in quad order planning uses this exact representation of polynomials that are separate in like X, Y, and Z, so to speak, because of the differential flatness property. What we've done is take it a little bit farther and say that that representation does tell you what control inputs to apply to track that trajectory, but you still don't track it perfectly. Like if you look at Ezra Tal's work with Sotak Karaman, they're tracking these same types of trajectories, but they're really, really high acceleration. And the minimum tracking error they can get is like 8 centimeters on a good day with no wind. So what I want to do is say, like, yes, we have all these beautiful controllers, beautiful trajectory plans, but we have to compensate for the fact that our description of the robot is in some ways imperfect.
I understand the difference, and of course I see the value. My question was really like more practical. So why don't you throw the U angle as well in the representation?
Oh, there's no reason. You get it kind of for free because the reachability does, you do reachability in one dimension, and then you concatenate the zonotopes to produce a reachable set in higher dimensions.
Got it. Okay. Let's see. A clarification, which I think is useful also when you started thinking about or showing results with moving obstacles. Can you clarify what happens offline and what happens online here? Yep. In the sense that, I'm imagining we are doing perception with our algorithms, we are getting this map in real time. Can we just use this real-time map to implement your algorithm?
Yes. So what happens offline is basically this. We compute a reachable set over like several time intervals. And here's a cartoon for a car. And then what we do at runtime is, given a prediction of another occupant of the world, we split that up into matching time intervals. And then we compare, so we basically treat the obstacles as static in each time interval. And then all the math that you already saw applies. So the only thing that has to change is how you hold on to time in your reachable set. Does that answer your question? It's just a slight change to the reachability computation offline, and then an assumption that the predictions at runtime are correct. meaning that
Can you comment on the computational cost of these two phases?
Yeah, so this, for the robot car, this is a bit more expensive than the static case because we have to hold on to time. However, it has been tractable for those wheeled robots. For the zonotope representation, it already partitions time into these intervals, so you actually don't pay any penalty offline. At runtime, and this is actually the partially why I've moved to the zonotope representation. At runtime, if we're not using the zonotope representation, we have to turn our obstacle predictions into a bunch of discrete points. And then each of these, so if this is the obstacle in a prediction, the prediction becomes a bunch of discrete points, and then each of these discrete points becomes a nonlinear constraint for our online optimization. So if we don't use zonotopes, this can explode in the number of constraints, which can really slow us down. However, for the zonotope representation, because our predictions are already defined over time intervals by assumption, the only difference is where the obstacle is relative to our reachable set for each time interval. But the projection into the parameter space is exactly the same. So we don't actually pay a computational penalty in that regard.
Got it. Okay.
So speaking of different representations for different objects,
Mm-hmm.
if you have a very non-rectangular obstacle, like say a door or a window, how would you represent that with zonotopes?
What we've done for the robot arm has been to decompose that into zonotopes, but we've done it manually. And this is exactly why I'm really curious about learning how to do representation guided perception. I believe that you can do a convex decomposition, and zonotopes are quite general. It's not immediate to me how to do it, but I think for example, for a door, which I would say a door at least is, the door itself is a cuboid, which can be represented as a zonotope or a convex polytope. So in general, I have been convinced that you can use things like occupancy grids or voxel grids that can be turned into these representations.
So let me ask a follow-up question on that, because at some point I looked at the expression of the zonotope and it seemed fairly general to enable stuff which is not axis aligned. But then you also decouple, I think, the optimization in the different dimensions. So the question is, can you allow the zonotope to be not to be axis aligned? Yeah.
Let me show you. I don't have slides for it yet, but if you look at this, the reachable set is this gray blob. I don't know how well you can see it, but this is a bunch of non-axis aligned zonotopes.
Perfect.
And our reachable sets for the arm, actually, it's really cool. We have zonotopes in the space of rotation matrices that are over approximating rotation matrices, and then we multiply them by volume zonotopes and produce conservative approximations of swept volumes. So it's not just that these don't have to be axis aligned, it's that we can apply rotations and transformations to them while still holding on to zonotope-like objects.
Very cool. I have another question, which is more of a comment rather than a question. I think you said safety does not require a global map, which is kind of an interesting comment, but at the same time, achieving a goal requires somehow like a global map in most of the cases, right? So definitely. I think it's the same difference within local reactive planning, let's say potential fields, and global path planning, right? You can avoid local obstacles, but with the local reactive approaches, you may get stuck, right?
Yes.
For example, you just get too conservative and you're stuck forever like in front of an obstacle rather than realizing that you have to plan over a longer horizon.
Right.
So any comments about that?
Yeah, in some ways we've solved that problem. Part of it is that, as I mentioned, we're sitting at that trajectory planner level. And so your path planner is allowed to do whatever it wants. So you could run an RRT that completely ignores the dynamics and can find, if it knows a map, a globally optimal solution if you're running RRT star eventually, right? But then you're trusting RTD in our case to track that global plan reliably. So in that case, for global optimality, yes, and reaching a goal, you do need a map. But like you're saying, for local reactivity, you don't. One way we've addressed this is, and I'll show this demo that compares, okay, here we go. So here is the Segway robot. And it is tasked with driving to this black X over here. We are solving the trajectory optimization at runtime with two different methods. One is fmincon in MATLAB, which always gets stuck in local minima. But like I said, as long as fmincon converges to a feasible solution, we're at least safe. And then the other thing that we've implemented is a Bernstein algorithm that can do branching and bounding of a polynomial optimization program to find a provably optimal solution in finite time. So that means that we can solve faster and always find the best solution. And I'll show you what it looks like on the robot. So here's planning with fmincon, and it just does a really bad job. The robot doesn't crash, but it immediately gets stuck, as you can see. So I have to actually drive the robot. Here I drive it out of this local minimum. The reason it's getting caught is that the cost function is bad in the sense that the cost function is just minimizing that distance down the hallway, right? So as soon as it hits this wall, it's like, I don't know what to do. We switch to our parallel constrained Bernstein algorithm, or PCBA. And this is the first take, and I didn't even pick up the controller, I just did it. So this is from our trajectory planning side, how we're solving this problem. But I think you have to bring both things together. You have to consider the global map if you care about reaching global goals, and then you have to pick the best trajectory optimization solver that you can.
Excellent. Okay, so I see a question from Hank. So maybe Hank can unmute himself and ask.
Yeah, so a question about when you do the reachability analysis, you have this drawing that you know, it looks like a sphere, and then you sample. You first over approximate with the zonotope, and then you sample the corners, and then you keep sampling the corners. I think in this way you're also overestimating your reachability zone, right?
Correct. So what we actually do in practice is we chop up that box into many small boxes, and it takes about 30 minutes for what this ends up being is actually, it is a lookup table in MATLAB, and it takes about 30 minutes to solve for that high dimensional model. But what we do is we split up the initial velocity box into a bunch of little boxes, and then at each little box, each corner, we take all these samples.
Okay. So is it guaranteed that you only sampling the corners will guarantee that you don't miss any arbitrary like corner points, right?
Right. And we also, I mean, the thing I didn't show is that we bound everything by the maximum velocity and maximum acceleration. So we're not actually doing the full box, we're bounding everything. But the reason it works is because if our rotation dynamics are faster than our translation dynamics, which is in general true for these types of robots, we can say that our tracking error, we can show that our tracking error will achieve a maximum given our trajectory parameterization by choosing the largest initial speeds. So like if I take, let's say this little box where the V naught is, and then I look at the magnitudes of all of these initial speeds, I know that the tracking error will be largest at the corners of this box rather than anywhere inside the box.
Okay.
Does that answer your question?
Yeah, but how conservative with this zonotope representation, right? Because by using zonotopes, you over approximate your reachability zone, and you also over approximate your obstacle. But in this case, I know that it's guaranteed to be safe, but how conservative is this, right? Are there cases where over approximating will lead to just no solution, but indeed there might be a solution, right? Is there any cases like this? Or how do you mitigate this issue?
So the way that we've mitigated it is by the finer you discretize your initial velocity space, the more resolution you have, and the smaller, the more you have the chance to, if you achieve a slow initial velocity, your error will be much smaller, right?
Yeah. So this is like a trade-off between computation, like performance guarantee and computation, right? But have you all ever thought about, I know there is work that instead of using zonotopes, they define these, maybe you can, I think definitely you can define these obstacles by using something called the, I don't know, it's like at some point you define it by using some polynomial equations. That is like cheaper, but can be more accurate because those are not just polytopes, right? I think it's by Brian Williams' group, the postdoc there, Anchor, I forgot his name. Like they use these type of semi-definite constraints, or maybe some other polynomial constraints to represent these uncertainties. Will that do any help to this?
We found that the zonotopes are less conservative. So actually, for all the wheeled robots, I didn't talk about this, but we solved the offline reachability using a semi-definite program, and it spits out a. So here's, I mean, don't worry about this stuff. This is what turns into an SDP. What we have is like points and parameters turn into a polynomial that is greater than or equal to 1 when you would have a collision according to that parameter, right? And then what we can do at runtime is, like I showed you here, we turn an obstacle into a bunch of points, and then we can evaluate our polynomial W on each of these obstacle points. And then this becomes a list of polynomial constraints produced by a sum of squares polynomial that is spit out by a semi-definite program. Just to give you context for like, we've also kind of explored this idea.
Okay.
The conservatism tends to be higher in this case because these SOS programs tend to be quite conservative in how they estimate the reachable set of the robot. But the other way I want to address that is like what I said about this data-driven reachability idea. I think that we can use clever statistical methods to reduce the size of the zonotope where we know we're not going to actually explore the space. Like suppose that our drone is flying and we're collecting data about what moves it made, then we know how bad of a job it did in practice, and we can update that lookup table that we computed offline to compensate for the fact that maybe our tracking error is not as bad as we thought. So here it's a bit of a more dangerous trade-off in the sense that you would immediately abandon safety guarantees, but you would directly address conservatism by adjusting your reachable set at runtime. And SOS programming doesn't let you do that, at least that I've seen.
Okay, great. Thank you. Thank you. Very interesting.
Thank you.
So Shreyas, thank you so much for the presentation. I think we have to stop here in the interest of time, but really appreciate it. I'm inviting the others, if they have more questions, just to reach out to you and ask technical questions about these. I think there might be even a question from Hank on polynomial optimization, because he's doing a lot of polynomial optimization on his side for perception problems. But thanks for your time. Really appreciate it. Cool talk. And,
thank you so much.
And I will see you soon, hopefully in person.
I hope so, yes. Thank you so much. And it's nice to meet everyone. I can stay around for a few more minutes if others have questions, but if you need to leave, go ahead. I will
stop the recording now, but I will leave the chat open if you guys want to keep chatting. Okay.
Great.
Thank you again.